Alright, so we're talking about logic applied to line diagrams. Now, we've talked a little bit about this before, but we're going to go into a little more in depth than this. The reason for that is because if you ever take the motor controls, sensors class, or a PLC class, this is the kind of diagrams you mainly deal with, right? So typical electrical control systems consist of two subsystems or circuits. You have your control circuit, which runs between 24 volts and 120 volts. And it's safer to deal with versus the power circuit, which runs the line side and runs 120 plus. Now, why is that important? Well, a motor can run on high voltage, but is it something we want to put our hands near? High voltage is not something we want our hands anywhere near. Mainly because high voltage tends to run 240-ish plus. Not exactly something you want to come across, right? I don't know about you, but fried person does not appeal to me. So this is pretty typical. In this particular one, you have your controls versus this is the actual wiring for the motor. Like I said, the motor typically runs on 240 plus. Your typical control circuit runs 24 volts-ish. Can run higher if it needs to, but generally we try and keep it at a lower rate. Why? Because it's safer, it's better to deal with, and if something goes wrong, it doesn't go majorly wrong. When you have the higher voltage you have, the higher amperage you can have. The main thing with that means the more heat you have. So your components have to be a little more robust at a higher voltage, right? But this is fairly typical right here of a control element. These components are fairly small, fairly delicate. Do we want to put something like this on a high voltage circuit? No. You would melt it. That would not be good for your circuit. So generally, the reason we put control at a lower voltage is because we really do not want to melt our components. Because most of the time, what are we trying to do with a lot of control circuits? Do we want them to be really, really big? Or we want to kind of try and keep them small. You want to keep them small because you don't want one machine to take up a whole room. We want one machine to take up one little section of the room and no more. But part of it has to pull a high voltage. Means you got to be real careful how you set up that circuit. So ladder diagrams or line diagrams, as a lot of people tend to try and call them. You have two vertical parallel lines that represent your hot and your neutral. Okay? Individual circuits are called rungs and are connected between these two, like we've already seen before. So on your hot side is where all your control is. On your L2 side, that is where your loads are. That is a hard and fast rule, guys. There should never, ever, ever be any more than one load per line. Why that rule exists, could not tell you for sure, but it is the big rule for this. And it truly does kind of make sense because the more stuff you put in a single line, the more confusing you're going to get as to how to wire it. Does that make sense? So loads must be connected in parallel if you're connecting more than one to a set. and just to show that yes, they are connected, but they are two separate loads. You don't want them on the same rung because you start putting too much on that same rung, it's going to get confusing. It's going to get hard to draw. It's a lot easier to make a mistake when you're trying to actually wire this in field. Because if we take a look at this previous one right here, this looks like the light should be directly connected to the solenoid. Don't really want to do that because the light has to have its own set of voltage. That solenoid has to have its own set of voltage or else the two don't work, right? So if you take that versus this, both of these are running 120. For those of you that have taken Intro to Electricity in DC, what happens when you put loads in series? What happens to your voltage? Huh? Voltage splits. It adds whenever you're trying to get to your total voltage mathematically. But technically what happens is your voltage splits in series. So if both of these need 120 to run, and I put those in series, how much is each one getting? They're only getting about 60 volts. Are they going to work? No. When you put them in parallel, your voltage stays the same. Does that make sense? So in this way, I can give both 120. If I put them both on the same line and try and put them in series, you're going to end up with 60 volts apiece and they will not work. Does that make sense? Yes, no, kind of? Okay. So if you're going to connect more than one load, they have to be in parallel. If you try and connect them physically in series, they really will not work. They just won't. So control relays, solenoids, and pilot lights are loads that should be connected to your neutral side. Again, one is hot, two is neutral, and then everything's connected between them. And since they're loads, they should never be connected in series. All right, so controls contacts don't usually run loads in the power circuit. How many of you even know what a solenoid is? Have ever actually seen one? A couple of y'all? All right, so you might end up having to correct me if I'm a little wrong on this. So basically what a solenoid is you have a piece of you have some winding wire that runs a current through it. And through this, you generally have a piece of metal. Now that piece of metal is magnetized. Okay? So when you run the current one way, you magnetize the wire one direction. And it will cause the rod inside that coil to either move one way or the other. So in order to move it the other way, you either have to remove power or you have to force the current to run the other way. Does that make sense? Let's see if I can draw it a little bit better than I can speak it here. So here's your, we'll call this north, we'll call this south. So that's magnetic. Around it, we have a coil of wire. Okay? So when I turn this on, this magnetizes so that it is north to south. What happens to it? is it's going to move this rod in the middle. If I move it instead to where it is south-north, it moves it the opposite direction. That is the very basics of how solenoids work. You don't really get to see a lot of that, mainly because we tend to put these inside devices, make sure that you can't touch this wire. Because if you're running 120 volts on that, you want to come across that? Nah. So most solenoids are packed away in these little boxes like this. And about the only thing you see is the spring on the outside and the metal rod that comes through. But it just basically works on the principles of magnetics. Does that make sense? So magnets either attract or repel, right? That's the basics of how a solenoid works, is it works upon magnetic principles. So that wire is either running a way to attract the rod one direction or the other, or it's looking to repel it in the opposite direction. Okay. Magnetic motor starter coils. So a lot of the times we put overload contacts between our load and our neutral line. Why? Well, because those particular coils help protect your devices. And if something goes wrong, it breaks it before you end up with your power moving all the way through your circuit. Because a lot of your voltage gets used up by these motor coils. So if it does so, and you end up with an overload moving through it, I'm not explaining this very well. Okay, so overload contacts worked upon the principle of excessive current. Okay, just like a fuse, just like a circuit breaker, if you have excessive current being pulled through either one of those, what happens? It breaks the connection. These overload contacts are meant to do the same thing. Okay? If your motor coil starts pulling too much current and passing too much current through itself, these coils are supposed to say, hey, 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 you can't do that. Continue doing it, done. Why? Well, because we really don't want to burn up our motor or any of the other components in our circuit. Okay? Does that make sense? A little bit more? So those basically are the guardians saying, hey, you can't put that much current through here. Because do the devices before it know what they're doing? Not really. They're just there to pass the current along. Okay. So we connect motor contacts before we put in overload contacts. Okay. That's pretty much the reason why. So a lot of things tend to have internal overload systems, especially motors. Because what happens to a motor if you overload it? You put too much electricity in a motor, what happens? It can speed up, yes. That's one thing. What else? It goes beyond its ratings, but okay, so this is essentially your motor right here. All that is nothing but copper wire. You overheat that, what's going to happen to it? It's going to melt. Oh, it's gonna melt. It melts. Your motor is useless. There is no coming back from that. Okay? So we put overloads in it because we do not want that motor overheating. The more heat it carries, the more likely you are to start melting that internal wire setup. You melt that internal wire setup, your motor becomes a useless piece of junk. Okay? Does that make sense? That's why whenever your computer heats up too much, what happens when your computer heats up too much? It clicks the fan that's internally set up on it on before it starts melting any components or it starts melting the solder that holds the components together. Heat is your enemy. You always want to make sure you don't have too much of it. This is your typical motor starter relay. This particular one is a magnetic motor starter. And you have your overloads that are actually built into this particular one. Should look familiar for those of you that have ever taken motor controls. So when the motor starts pulling too much current, this guy says, no, 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 you're not allowed to do that. Continue pulling it. Okay, well, I'm turning all power off on you. We typically rate these right at the threshold for the motor. You don't want to overrate them because if you overrate them, just like if you put a fuse that's too big in, you're begging for trouble. But you also don't want to put something too small in because when the motor starts up, it's got to pull a certain amount of current. Okay? Just like your car, right? Whenever you first start it up, it's sucking up the gas. It's trying to turn itself over, and it takes more work for it to start. Right? Kind of like what takes more work for you to start. Taking that first step or continuing walking. Which one takes more energy? Taking the first step. Getting up off the couch and taking the first step. Same thing for a motor. Taking that first step, getting up off the couch, takes it a minute. So it pulls excessive current for that 1 minute. That's fine. But continuing to pull it causes a lot of problems down the road. So we have these guys in line with the motor contacts to prevent overload. Okay? Control devices and loads. So control devices are connected between L1 and the load. We've already said that. Electrical loads are connected between the control devices and L2. The only thing allowed between those devices of the load and L2 are overloads. It's the only thing you're supposed to put in there. And again, that's so that if you start passing excessive current, it's got some way of saying, I'm not doing that. So control devices are connected between L1 and the operating coil. Here. Again, it's just reiterating the fact that you put your control devices first, your loads second, and any overload contacts third. Okay? So these are some different loads. You have your typical control devices. You have your push buttons. You have your what? What are these guys? Those are limit switches. A very common type of sensor, right? What do? They basically are the counters and operators. There are remote devices that can do a lot of things. Okay. You got another limit switch, but this one's a smaller device. Yeah. So two control devices may be connected in series or parallel to control a coil in a magnetic motor starter. These do not really need voltage. What do? You don't need voltage. If you don't need current, then you're not a load. You're a control device. And your basic job in life is basically to pass the buck. So what you're trying to do is you're trying to make or break contact. Whenever it's broken like it is here versus made, this air gap is generally just enough to make sure that your voltage and your current cannot jump. Now, over time, that wears out, and they actually don't open all the way to the point where you do have to replace devices. But when they're open, you cannot pass voltage or current, theoretically. Now, if you put too much voltage and current in, can it jump the gap? Yeah, it's called arc over. It's not exactly a good thing to have. Whenever it's closed is when it actually passes voltage and current to the next setup. Okay? So we use these to control our loads. Okay? And we can put it in a couple different configurations depending upon how we need to get everything started. For those of you that have taken motor controls or PLCs, what kind of logic is the first one? It's AND logic. AND logic. So it means that you have to have your flow switch closed and your temperature switch closed before you're able to start your motor. What kind of logic is this guy right here? It's what's called OR logic. For those of you who've never dealt with logic, it just means that either one of these particular switches can be used to start your motor starter. Okay? Does that make sense to everybody? I lost anybody? Any questions at all? All right, moving on. All right, so you got your typical foot switch and a couple other sensors here. Each line in a line diagram should be numbered, starting with the top line and reading down. Basically, it's a way to create references for yourself. Why? Well, because if you don't have references, when you're trying to find something later in a blueprint, how hard is it? You have no reference point to start from. Kind of a pain, right? The whole reason we do it is to create reference numbers for ourselves, save our sanity. You know? If you can never save your sanity, why not, right? Locations of normally open contacts controlled by a device are determined by the numbers on the right side of the diagram. So we are able to create a cross-reference. So not only can I look at this particular diagram and say, well, I've got all my numbers, so all I've got to do is look for my reference points. I now can also say, oh, I've got a control relay 2 here. If I look over here to the left, I see that I have lines 8 and 10 referenced back to this. So if I go to line 8 And I look across, there's control relay 2. Its normally open contact is being used here on 8. Well, I've also got to look at 10. Hey, there it is again, another normally open contact. What that means is that when this switch is closed and the control relay is energized, that means that these two contacts on 8 and 10 will close. That will energize the pilot light on 10 and the motor coil on 8. Does that make sense? They're just reference numbers to tell you, hey, this is also here and here. So you can look at it and go, oh, if I energize this, I might need to make sure that these two circuits are clear from whoever's messing with them. Because are all these circuits going to be right next to each other? No, not always. You could end up with one circuit that's on the other side of the plant, right? So you really want to be careful when you're starting stuff up. Otherwise, you could shock somebody. I find that most people tend to not like getting shocked for some weird reason. All right, so normally closed contacts are indicated by numbers that are underlined. So whenever we use the contacts that are normally closed, we underline them on the left. So our reference number tells us, hey, that's a normally closed contact that will open or disengage whenever the contact it's connected to is energized. Okay? Does that make sense? Okay. So each wire in a control circuit is assigned a reference point on a line diagram to keep track of different wires that connect the components in the circuit. I would like to say that this is completely true, but it's not. Especially if you start getting into older pieces of equipment, it's not always labeled. Okay? That or if somebody starts monkeying with it, are they going to remember to go back and label it? Probably not. So whenever you're trying to look for reference points, yes, diagrams are a good way to go. That's why you also grab the blueprints and anything else you can grab hold of to try and track and trace. Why? Because if anybody's done any kind of work or touched it in any kind of way, especially when you're in field trying to install things, do you always remember to do everything you're supposed to do? Everybody just shake your head no, because we all know it can be really hard and stressful whenever you're trying to install something and you're just sitting there going, dude, move. I've got to put these plugs things in and all this other stuff, right? So that does not mean that it will not be there, but it may not be there and done correctly. So that's why not only should you look for the reference numbers, but you should also be looking at, oh, well, I've got L1, I've got L2. And between them, I should have a push button and a control relay. Okay, let's look for my push button and my control relay. Are these wire numbers correct? They are? Okay, good. All right, control relay also goes down to lines 5 and 6. So I should have a control relay contact looking at a motor control relay. And I should also have an open control relay with motor contact 2. And these are the wire numbers they should be connected to. So always make sure you're looking, if you're doing this, it is good to know if the wires are correctly labeled. But you should always take anything you see with a grain of salt. Does that make sense? Don't take it for gospel and say, oh, they labeled it, yay. Always sit there and go back and look at your actual devices and say, okay, which ones are rich? Okay? Always use caution. Because how many times is a blueprint changed? The blueprint itself? Almost never. The notes on it? Every now and then, right? Somebody remembers to actually do their paperwork correctly. Always take it with a grain of caution, guys. While it's nice if they do number the wires, you cannot guarantee it. Because somebody goes in and does a quick repair, changed out a wire, the chances of them remembering to label said wire aren't the best in the world. Manufacturers include terminal numbers to identify and separate different component parts, including individual pieces of equipment. That is something you can guarantee. Guarantee that somebody actually wrote it down. You got a pretty good shot if they actually paid attention. So you got control relay, you have 2 and 10 that energize that relay. Okay? And then it comes over here and tells you 1 and 3 are used here, 6 and 5 here, 11 and 9 here. This is your typical setup for a control relay. So 1 and 3 should be a normally open, 6 and 5 should be a normally closed, and 11 and 9 is a normally open. Okay. Contacts found in different control lines that belong to the same control switch are illustrated using dashed lines or numerical cross-reference. So the dashed line saying, hey, if one's closed, the other's open, can be used. You can also have these little reference numbers. When one's energized, the other de-energizes. All right, so you should always have a signal, a decision, and an action. I mean, that's pretty self-explanatory. Between L1 and L2, you should have some sort of something telling your circuit, yes, you're on, no, you're off, right? Then you have something that's going to be doing something else. You have your load. In the action section, there's not always something that's making a direct decision, though. You do a very simple circuit where you just have a push button and a motor relay. You don't really have something that's trying to make a decision. You just have something you're turning on. Okay. All right, so we have what's called logic. How many of you are familiar with the terms logic and the basic 5? Technically there are 6, but we call them the basic 5. Because then you have one that's typically forgotten. So what is logic? How many of y'all have ever heard of it? Just kind of raise your hand real quick. You have the 5 basics plus memory. You have and. That's what this guy has right here. Basically, it means that. How many of you have ever seen the movie where, I mean, this is like used in 1,000 movies. In order to activate something, you have to have 2 people with the key, or both people have to push the push button, right? We need to energize this. Well, I need you to come here and help me both. We have to push both buttons, and they're on opposite sides of the room. Y'all know what I'm talking about? That is AND logic. In other words, this particular solenoid will not energize without both buttons being pushed at the same time. Okay? Now, why would we want something like that? Well, it could be a safety measure, making sure that both hands are out of something before anything's allowed to start. Right? Yeah. One of the basic ones I can think of is, okay, so here you are, you've made this item, you're about to send it on, but to make sure your hands are clear, or the employee's hands are clear, they have to put both hands on a push button right here to say, hey, my hands are clear. It's known to work. Why? Because it's a very simple and easy way to create a relay control that says, hey, well, this person's done with their job, their hands are clear, they're not going to get their hands caught anywhere. And if they pull their hands off, the circuit opens and their hands cannot get caught in mechanicals. Right? So you can see where something like that could be very important. Doesn't seem like it, but it can be. Then you have OR logic. So that's essentially the function a lot of people try and use, where let's say I have two different control systems controlling a central machine. One's on one side of the room, one's on the other side of the room. It just means that either panel can be used to activate my center machine. Okay? That's OR logic. Give you some real world scenarios there. So the decision section of any circuit may contain one or more logic functions. In this case, they're showing you two ands, or I'm sorry, they're showing you AND logic as well as OR logic. One of the logics is not logic. We typically use this in what kind of circuit? Those of you that have taken motors or PLCs. What do we use not logic for? What is the most typical thing we do with not logic? It's a device that should be on every piece of machinery. An e-stop, right? You can turn around and look. You should see a bright red button on everything that's got a blue face to it over here. Those are your e-stops. Those should not be engaged unless you push the button and then it disengages, right? The whole purpose of them is to say, hey, break the circuit. There's something going wrong. We need to stop everything. Okay? Then you have NOR logic. This would be multiple e-stops. Why? Well, maybe we need to have not only an e-stop on one, so like our assembly line over here. Any one of those e-stops will stop that line. Any single one of them. I don't care if you're looking at the section for the robot, if you're looking at any one of the assembly sections. It will stop the line. Why? Well, maybe I've got a collision somewhere. Maybe something has gone kind of funky and it needs to be fixed. That is NOR logic. Okay? Then you have NAND logic. Okay, NAND logic's a little bit interesting because it has to take two switches or more in order to stop the operation. Because maybe somebody happened to just lean on something the wrong way, right? Do I want my circuit to just stop because somebody leaned on something the wrong way? Nah. Another way you could have this is, let's say you have a light curtain. Everybody knows what a light curtain is, right? Anybody not know what a light curtain is? Okay, light curtains. Simply put, a light curtain is basically these rows of laser beams and receivers on either side. All right, basically like a laser gate. Does that make sense? So if you break the gate, it's supposed to stop all operation. You know what I'm talking about? Okay. So in order to stop a machine from running, maybe you don't just want the gate broken, but you also want somebody to press a button to say stop the operation. Not because, oh, I happen to, just lean into it a little bit. So you want a double stop safety set. Just to make sure everybody's doing what they need to do. There's a lot of reasons and a lot of ways you can set a lot of these up. So one of the things you should have seen with some of these are what are called auxiliary contacts. That's these guys right here. The whole purpose of that is for the sixth and often forgotten mode of logic, and that is called memory. The whole purpose of memory is to create a sealed-in circuit so that it continues operation without you having to sit there and hold the button or sit there and hold the switch. It seals in and says, okay, I will continue operation even though you have released me. Okay? So that is the sixth one. That is memory. Does that make sense to everybody? Are there any questions so far? I'm up here walking and I fall on my face. Is everybody going to laugh at me? So a common start-stop control circuit is created by adding the NOT logic of a stop-push button to the memory logic of a so I'm going to simplify this. This is a very typical setup for a start-stop circuit. We don't want anything stopped unless we push the button to stop it. But once we start it, we want it to seal in and keep it running until we tell it to stop at the same time. Does that make sense? Just to simplify and boil that down. Okay, it's using memory as well as NOT logic in order to keep your circuit energized. Okay. So in this particular one, they've got 2 stop push buttons as well as 2 start push buttons. So they've got AND logic and OR logic set up together to create the circuit. Again, this goes back to having 2 control panels. Either control panel will start my motor running. Okay? And this is how I would set that circuit up to do so. Using memory as well as NAND and OR logic. So again, this is just showing y'all some examples of all this, guys. So this one is how they've set it up to create, make sure I'm saying this right. So they've got 2 different circuits to run 2 different machines. How do I know that? Because I've got a motor coil here and a motor coil here. Motor coil 1, motor coil 2. I've got one e-stop that will stop both machines if necessary. I've also got 2 stop buttons to stop them individually. I've got 2 start buttons to make either one run, or I can make them both run. Okay. This is very common to have e-stops that can stop a whole system. Why? Well, because if one thing's going wrong, how's the chance of most of it going wrong? Kind of like Murphy's Law, right? Anything that can go wrong will go wrong. So if you can prevent Murphy's Law, or you can stop it mid-law, why wouldn't you set up to do so, right? If you have anything that jams, if you have anything that all of a sudden gets twisted the wrong way. It's a good thing to have an e-stop set up everywhere so that you can make sure that nothing gets messed up. All right. This particular one, they've got a secondary motor coil, but it will not energize until you energize the first one. And it's talking about product separation or stretching. Now, what does that mean? Anybody know? Product separation or stretching? All right, I'll give you an example. Over here on either one of these lines, if I start one piece, I want to start it all. Okay? Why? Because I don't want it getting stuck in any one place and creating what's known as a bottleneck. Everybody knows what a bottleneck is, yeah? So separation or stretching is basically talking about an assembly line. So with an assembly line, let's say I've got two parts of my assembly line. I've got section A. Let's say this is X product. And then we have section B with its set of product. Now, I don't want section A running without section B running. Why? Because I want to make sure that as soon as section A is done, I don't have everything trying to back up right here at this point, because section B is not running. Does that make sense? That's about the easiest way I can say that. So product stretching or separation essentially means that I don't want section A running without section B running, or section B running without section A running. Okay? All right. Pilot's light is used with a pressure switch to indicate when a device is activated. We put pilot lights on a lot of things. Why? Because we want to know that a machine is running, right? Why do we want to know the machine is running? Well, we don't exactly want somebody walking up to it and going, hey, this isn't running. And it is. Biggest example and best example I can tell you is, if any of you have been next door, you've seen the giant yellow robot, or you could even see these two robots. Believe it or not, these robots are actually active. The big one isn't, but these two are. These two can be totally active, but they're sitting in that same position. Why? They're doing what's called perching. And what that is essentially doing is it's waiting for a signal. Any kind of signal saying, hey, you need to go to work. And then all of a sudden it moves. Now, on something small like those, not such a big problem, right? Something on that 1-ton behemoth in there, you see the issue, right? A lot of people have been hurt and killed by robots because they go up to it going, oh, it's not running, trip a sensor. And all of a sudden the robot goes, woof, person goes, wee, through a wall. Okay? Yes, I'm trying to make it humorous because I don't want y'all really stopping to think about that for a minute. Essentially ends up crushing you like a bug. Okay? So we put pilot lights on a lot of machinery just so that somebody can sit there and go, oh, this is actually on. I probably don't need to go anywhere near this thing, right? That is the main purpose of that. That or to say, hey, this is off. It is safe to approach. Depending on the machine. All right. I'm trying to get through some of this, guys, so I'm going to try and jump ahead a little bit. A lot of this is just redoing the same thing, only instead of motor coils, now we've got the pilot light. All right. Like I said, the whole purpose of a pilot light isn't so much to light anything as it is to sit there and give you a visual signal saying, yes, this is actually active. You might not want to be right here. Okay? This particular one's a sequence control circuit. Again, it's just to try and prevent stretching a product or running a machine whenever it's not got any product there. Okay? Keep everything running smooth. All right, this one's using a selector switch. You've got an industrial circuits that run or jog. What does it mean by run and jog? Well, run means that it's running. It's just doing normal operation. Jog is essentially, well, I don't know if this is running correctly, so I need to go back and run it in a slower pattern or in a controlled pattern to see what's going on with my equipment. Does that make sense? Any questions, guys? All right, and that is the end. Y'all got any questions on that particular set?